All right, today we're going to pull back the curtain on one of the most important, but also one of the most invisible technologies that makes our modern world even possible. We're talking about the digital armor known as error-correcting codes.
I mean, seriously, have you ever thought about that? How can a tiny piece of data survive a big old scratch on a disk, or a 250 million mile journey through the static and radiation of deep space? It kind of seems like it shouldn't work, right?
Well, it's definitely not magic. The answer is this incredibly clever, fundamental process. A hidden layer of armor that is protecting our information all day, every day. So let's dive in and see how it works.
To really understand the armor, first you have to understand what it's fighting against. And in the digital world, that enemy has a name: noise. So what is digital noise? Well, it's pretty much any random disruption that can mess with our data. We're talking about a solar flare, a scratch on a DVD, static on your Wi-Fi, anything that can flip a precious little 0 into a 1 or a 1 back into a 0. It's this constant, invisible threat to the integrity of everything we send and receive.
So look at this. This is the basic journey of any piece of digital information. It starts at a source, it gets encoded, and then it enters the danger zone, the channel. This is where the noise attacks. And the entire goal of this whole process is to make absolutely sure that the message that arrives at the destination is the exact same one that left the source in the first place.
Okay, so how do we fight back against all that noise? Well, the secret isn't just about making the signal more powerful, just trying to shout louder. It's about making the message itself smarter.
The solution is a concept called redundancy. It basically means adding a few extra bits of information to the original message. Think about trying to tell a friend your phone number in a really loud room. You might say the last few digits twice just to be sure they got it right. That's redundancy in a nutshell. But the codes we're talking about, they do it in a way that is just so much more sophisticated.
And this really shows the two different ways you could tackle the problem. On one hand, you have the brute force method. You could just send the entire message 3 times. Sure, it'll probably work, but it's incredibly wasteful. The other way, the smart structure approach, is to add a small, mathematically calculated check to the original message. It's elegant, it's efficient, and it is way more powerful.
So, how does this smart structure thing actually work? What's the secret sauce? Let's pop the hood and take a quick look at the brilliant minds and the core mathematics that made all of this possible.
This isn't some newfangled idea. It's a foundational pillar of the digital age. It really all kicked off in 1948 with Claude Shannon, who basically laid out the entire theory. Just 2 years later, a guy named Richard Hamming came along and created the first practical error-correcting codes. And from that point on, the whole field just exploded.
The core principle behind all of this is something called minimum distance. Okay, imagine a language where the only 2 valid words are apple and banana. They're very different, right? They're far apart. So if you get a garbled message that says bapple, you know instantly the sender must have meant apple because it's just closer. Error-correcting codes do this exact same thing, but with binary data, creating valid code words that are mathematically far apart from each other. And this isn't just a vague concept. It's all based on precise math. The minimum distance between any 2 valid code words has to be at least 2 times e plus 1, where e is simply the number of errors you want to be able to fix. That little formula is the bedrock that guarantees our data's reliability.
Now, this single principle was so powerful that it didn't just lead to one solution. It gave rise to a whole universe of different codes, each one a specialized tool for a very specific job. So yeah, there's no single master code that does everything. Instead, scientists and engineers have built this massive toolkit. Whether you're trying to send data across the solar system or just across your living room, there's a specific code that's been designed for that exact challenge.
And you can see these different tools in action all around you, every single day. Those Reed-Solomon codes, that's the reason your scratched CD still worked. It's how we get those mind-blowing pictures back from Mars and Pluto. LDPC codes are the modern workhorses. They're running your Wi-Fi, your 5G, your digital TV. And if we look to the future, quantum codes are being designed right now to protect the unbelievably fragile data inside quantum computers.
And honestly, that's just scratching the surface. I mean, the field is so incredibly rich. You've got dozens of other major types of codes like these. Each one represents a unique mathematical breakthrough designed to solve specific kinds of error problems with different levels of efficiency. It's really a testament to decades of brilliant work. Okay, so let's zoom all the way out. What does this all actually mean? Why does this invisible mathematical process matter so much in our daily lives?
It means that this entire digital world that we have built, the internet, global communications, all of our data storage, literally everything, it is not the fragile house of cards that you might think it is.
Here's the most important takeaway. Our digital world is resilient, it's tough, and it is that way by design. Every single time you stream a video, or make a phone call, or even just swipe your credit card, you are relying on the strength of this invisible armor. And I really can't say it any better than how the source material for this explainer puts it. They are the fundamental component. Without them, reliable digital communication as we know it would simply be impossible.
Which of course leaves us with a really fascinating question for the future. As we move deeper into the worlds of AI, quantum computing, and just ever-denser data, our information is going to get way more complex, and it's going to face new, unexpected kinds of noise. So the next great challenge is going to be designing the new armor that we'll need to protect it.